Okay, we have more or less finished it, but we will do some example. We will go into basically most of the things are for paper 5 lah. And these are the formulas that you need to remember and know how to use. Right? Usually they don't use Q lah, they will use P lah, because it's electrical heating. Then this is correct for heat loss lah. This rate, this heat loss lah. L is the latent heat lah. C is the specific capacity. Okay. Right. Paper 5, you got 2 questions. 30 marks or altogether, 1 hour, 50 minutes. Question 1 is basically like your paper 3 lah. Except paper 3 are given the instruction to carry out the experiment. Whereas question 1 is basically tell you the problem, give you a formula, and then you are supposed to tell the examiner how to conduct the experiment. So it's a bit harder lah. Anyway, the last lesson we stop at constant head pressure apparatus needs to give constant pressure lah. This is made of copper. There are 3 holes there. This one is for the water to overflow. And then you cannot see the water level, so you connect it to a tube, a glass tube there, so you can see the water level. And then this one can connect to the horizontal tube, study the flow rate or anything that require constant pressure. Right? Example, this apparatus, right? Liquid in, and then liquid coming out. There's your heater, connected a 12 volt back power supply, voltmeter to measure the voltage, ammeter to measure the current flowing through the heater. You don't need to know about platinum resistance, so you can use the mercury thermometer, graduated in 0.1 degree Celsius. Let the liquid flow at constant rate. Turn on the power supply. And then when the temperature is steady, right, look at the temperature going in and temperature going out. Right? This theta 1, this theta 2. When the temperature is constant, doesn't rise anymore, then you take the temperature. That's the advantage. Temperature doesn't change when you read it, not like other experiment. Then you collect the water coming out from here. For that M1 in time T1, and then theta 1 and theta 2. Then note the voltmeter and ammeter reading. Then heat gain, heat supply equals to heat gain. Right? Heat supply is by electrical method, V1 I1 T, and then M1 T theta 1 minus theta 2 plus H. Right? That's the heat loss. The advantage of the apparatus is the water is surrounded by a vacuum. This is a vacuum there, glass vacuum. Then you can change to V2 and V and I2, and the flow rate is changed to obtain the same temperature again. Right? Adjust it until you obtain the same temperature again, theta 1 and theta 2. Then you got 2 equations. Equation 2. Right? Same temperature, same amount of heat will be lost. C can be found by subtraction. Right? Subtract the 2 equations. And then we represent our Q as this one as Q. Okay, so Q1, Q2 minus Q1, Q2 minus Q1. We can take our theta out, M1, theta out. So theta That's where we get it. Take it down. H eliminated. And then M1 minus M2 minus M1. No? No need to worry about the derivation now. Advantage and disadvantage. Disadvantage, you use a lot of quantity of water. Wasteful lah. Advantage, heat losses. The presence of vacuum prevents heat losses by convection, and the effect of losses due to conduction and radiation is eliminated. Heat capacity apparatus is not required. Normally, when you use a copper calorimeter, you need to know the heat capacity of calorimeter. But this one, you don't need to know the heat capacity of the apparatus. The temperature which is measured are steady, right? It's constant, it doesn't change, and therefore can be determined accurately using platinum resistant thermometer or mercury thermometer graduated 0.1 degree. This allows small temperature rises, typically 2 degrees Celsius. They didn't have to go to high temperature. And this method is therefore suitable for determining the manner in which the specific heat capacity changes with temperature. I can use resistant thermometer rather than platinum resistant thermometer. Okay, let's go to temperature time graph for substance being heated at constant rate. Okay. There's your power times T is the heat supply, and MC theta 1 theta minus theta I rearranging. Right? Theta I is the initial temperature, theta is the final temperature, T is the specific capacity, M is the mass. Right? So rearranging, take MC down, got that, and take theta I across the other side, we got plus theta I. Okay, so that's what the symbol means. So this is the equation of a straight line with a slope. That's the slope. Right? Y temperature against time, temperature against time. So basically the slope is proportional to, is inversely proportional to C lah, capacity. So this one is usually the surrounding temperature, room temperature. You can write the equation down there, right? Where we take our C as a constant, B as a constant. So this is a straight line, no heat loss, no heat loss. So it's a straight line graph. That is just to derive for you the equation, show you the working involved. Okay, effect of heat loss. Theta I surrounding temperature, hot body, temperature at any time. Delta theta is theta as theta I. This is called excess temperature. Heat loss is directly proportional to excess temperature for forced convection. This is Newton's law of cooling. You don't need to know Newton's law of cooling, but they can state for you. And then you need to know how to write the equation. Right? So if heat loss, then in normal, there is no heat loss. It's a straight line. If heat loss, it will go into a curve. And at this part there, it doesn't rise the temperature anymore because the rate of heat loss equals to heat gain. Right? Whatever it gained from heat, whatever heat it gained, it lost. So there's no rise in temperature anymore. There's a rise in temperature for this part because it's gaining heat even though there's heat loss. This one, you're supposed to write the equation. And excess temperature, temperature above the surrounding. K is a constant. Theta is the temperature of the body, hot body, and theta I is the surrounding temperature. What is forced convection? When the hot body is forced to lose heat by blowing air across it using a fan, that's forced convection. What happens when the rate of heat gain is equal to the rate of heat loss? Temperature of the body stop rising. Right? This is natural convection, where you allow the heat to be lost by the vessel. This one is forced convection, where you have a fan blowing across a vessel or beaker or whatever container you are using, so that it lost heat faster. Right? So you need to know how to correct for heat loss. Right? We'll do some question to show you. Let's just summarize what we have studied for this topic. Right? It's supposed to be specific capacity rather than thermal properties. Heat flowing in becomes internal energy. Right? So that delta Q becomes delta U. Right? If no heat is lost. How do we know there's an increase in internal energy? Rise in temperature. Right? So where there's a rise in temperature, we use this formula to calculate. C is a specific capacity. Right? Know the definition, memorize it. And then if it's a straight line, where no heat loss, then C is inversely proportional to the slope. Right? Q, usually we use P, we use electrical method lah. So P equals VI, Q equals P times T. Right? So if it has a metal, U internal energy equals to sum of the kinetic and potential energy. So if there's a rise in temperature, it's this part lah. Kinetic energy is increasing. For solid, where we come to melting, then bonds are broken. No? As for liquid, where we want to convert it to gas, vapor, right? We have to do two things. Separate against intermolecular forces or forces of attraction and repulsion. And then expand into the atmosphere. Two things going to happen. So that is the potential energy part. For ideal gas, it has no potential energy, zero. Right? So remember the definition, sum of potential and kinetic energy of particles and random motion. The term random must be there. Right? This one show you the change in phase. Ice change to water. Ice change into, we are not interested in this stage, this sublimation. Right? This one we use formula latent heat to calculate. Fusion is for solid to liquid. Vaporization is for liquid to vapor. Right? Know the definition. Quantity of heat required to change the state of unit mass of substance at constant temperature. Important, constant temperature, unit mass. Right? And if you're supposed to read this graph, this is shown by the larger time, more heat required. Right? And this time solid to liquid is liquid to gas. In melting, energy is required to break the strong bonds between the molecules. In boiling, work is done to separate the molecules so that the intermolecular forces between becomes negligible. Separate the particles so that the force of attraction and repulsion becomes negligible. Then you are supposed to expand it against the atmospheric pressure to require work done. Right? That's why the latent heat of vaporization is greater than latent heat of fusion. Okay, I hope you have tried that. If not, you better try it. Don't want to go too fast. Okay, change in phase. You should be able to identify the portion is a solid heated up in a closed container. So you should be able to get this is solid, right? This part solid. This part is solid and liquid where it's melting. Then after it melt completely, this is liquid specific capacity. And when it's changing to gas, this is liquid and gas. So when it changes completely to gas, if it's in a closed container, you're still supplying heat, temperature will rise. Okay, any comment?
No.
The rest you can do yourself. Let's try this one. Have you been able to get the answer? Haven't tried.
Haven't yet.
Mass of 20 grams of water at 20 degrees. 20 grams of water at 20 degrees Celsius is cooled to ice at 0 degrees Celsius. The specific capacity of water is given. Specific latent heat of ice is also given. So the energy liberated as heat when water is cooled to water at 0 degrees centigrade. Right? This water has to cool from 20 degrees to water at 0 degrees centigrade. And then later on, it has to form ice. So from water at 0 degrees Celsius to ice at 0 degrees Celsius. So water cooled to water at 0 degrees Celsius, you use specific capacity, change it to kilogram, use specific capacity of water, and lose in temperature.
1680.
Say again,
Oh, yeah. Correct answer.
and now water at 0 degrees changing to ice and water to ice at 0 degrees Celsius, latent heat of fusion, right? Mass latent heat L. Always write the equation down. Don't want to write numbers. Just in case you code wrongly, at least you get a mark for your equation. And your total, you add the two energy. Right? Then time required to cool the water to 0 degrees Celsius. If the rate of heat loss is at steady rate of 32 watt, right? P is Q over T. So T 32 is given. Q we have calculated out. And then there's the time that we want to calculate. Can anything not clear?
What's energy liberated again?
It cool down, it cool down from water at 20 grams of water at 20 degrees Celsius. It cool down to form
But
ice.
what's the meaning of liberated?
Oh, give out, loss.
Oh, energy loss.
Ah, okay, anything else?
No.
Okay, if not, let's try another question. What mass of dry steam at 100 degrees Celsius needs to be blown over 1.5 kilogram lump of ice at 0 degrees Celsius to convert it to water at 21.5 degrees Celsius. Right? What have we to do? Why? Heat loss. Heat loss by steam has to cool to boiling water. Right? Steam at 100 degrees Celsius, cool to boiling water. This is a change in phase. And boiling water cools to final temperature, 21.5 degrees. Well, heat gain. Heat gain is gained by this one, ice at 0 degrees Celsius. Ice melt to ice water, change in phase. Ice water increase the temperature to 21.5 degrees. So I have to calculate step by step. Okay, Q1, heat loss by dry steam to become water at 100 degrees Celsius, latent heat. Right? Let the mass of steam be M. And heat loss by water at 100 degrees Celsius as the water cools to 21.5 degrees Celsius. So that one you use specific capacity. Right? There's your mass, unknown mass. There's a specific capacity, 100 minus 21.5. And heat gain by ice. Right? The two things. One is steam. The other one is lump of ice. So the heat gain by ice to ice water at 0 degrees Celsius gives latent heat of fusion. This mass of ice, that one is mass of steam. Put it in, latent heat of fusion is given, calculate out. Heat gain by ice water to reach 21.5 degrees Celsius. Use specific capacity. So M is 1.5. Specific capacity given. And then the rise in temperature is 21.5. Calculate out. That's why we have calculate. Heat gain equals heat loss. Heat loss by steam. Heat gain by ice. Can?
Hmm. Okay.
Okay, let's try something else. The rest you can try yourself. Okay, let's try 2015 June, paper 41. Sorry. An electrical heater is immersed in some melting ice that is contained in a funnel as shown in the figure 3.1. That's your figure. That's your heater. That's your melting ice. Heater is switched on, and when the ice is melting at constant rate, the mass M of ice melted at 5 minutes is noted together with power P of the heater. The power P of the heater is then increased. A new reading for mass M of ice melted in 5 minutes, you use the same time, 5 minutes, is recorded when the ice melt at constant rate. Remember, you need to know roughly the value of latent heat of vaporization and fusion of water, right? Just to know that your calculation is all right, lah. So that you know whether your calculation is correct. Okay, you should be able to do the first part. If you haven't done it, try it now. Data of power supply and mass are shown. How to calculate the mass melted per second. Can?
Okay.
You should get 0.26. 78 divided by 5, change it to second times 60, and you get your answer. Same thing, repeat for that one. So that is worth 2 marks. Try to show you're working. Use the data in the completed 3.2 to determine the value of specific latent heat of fusion of ice. How do I go about it? Any idea? What formula to use? Let H be the rate of heat gain from the surrounding. Right? You're melting ice, so you are going to get heat gain from the surrounding. So that's the formula that we are using. No? It's the heat supply, heat gain from the surrounding, M divided by MT divided by L, that's M divided by T. Rate of heat gain, rate of heat, that's the rate of heat supply lah. Sorry. Rate of heat gain is this one lah. Okay. Sorry. Basically, we are using this formula. Put 70 there. You know what happened to the slide here? Right? 70 into here. And then that is 0.26 times L. And then 110, 110 plus H M over T is this one times L. Then you subtract, and we get this equation. Can or not? Basically, that way lah, like that lah. Then we can calculate our L. The rate of heat, the rate H of thermal energy gain by ice from the surrounding. And we can use either equation to calculate your heat gain. Right? Either equation 1 or equation 2. So if we use equation 1, right, we have calculated our L from previously. And take this 70 across there. Okay or not? That equation should be here lah. We are finishing off in 10 minutes time. You have to be flexible lah. Right? Sometimes we plus H here because there's a heat loss to the surrounding. But in this case, it's heat gain from the surrounding. That's why we put a H across there. When the answer is negative for H, it means that the rate of heat is gained from the surrounding. This one is heat loss. So you get a negative answer, then you know it's heat gain from the surrounding. Okay. The resistance of a thermistor, written there for you, at 0 degrees Celsius is that, at 100 degrees Celsius is 190 ohm. When the thermistor is placed in water at a particular constant temperature, its resistance is that. Assuming that the resistance of the thermistor varies linearly with temperature, calculate the temperature of water. Basically, they are using this formula, using proportion. So the mark distribution is just basically right, that proportion equals to that, correspond to that proportion. That's what they are saying. And then for this part and this part is 230, 2300 ohm. So the temperature is basically using this formula. Right? Take 100 across there. And this one minus that, which is this part. This one minus that. Okay, get 42 degrees Celsius. Can or not? Anything not clear?
Okay.
I suppose you can use formula easier lah. Use proportion no? Rather than this one. This is the mark they give lah. 1 mark here, 1 mark here lah. Okay. Temperature of water as measured in thermodynamic scale is 286 Kelvin. By reference to what is meant by thermodynamic scale of temperature, comment on your answer in one. Answer in one is 42 degrees Celsius. So how to comment? First, convert to Celsius first. From Kelvin is 13 degrees. Right? Different from 42 degrees. So you have to comment on why the two values are different. Right? Thermodynamic scale does not depend on the property of a substance. So change in resistance thermistor, basically the change in resistance of thermistor with temperature is non-linear. That's the reason. Can or not?
Hmm.
Okay, let us make a start. A polystyrene cup contains 95 grams of water at 28 degrees Celsius. A cube of ice of mass 12 grams is put into the water. Initially, ice at 0 degrees Celsius. Right? Draw a picture there so that you know what's happening. Right? That's your ice cube. 28 degrees is 25 grams of water. Assuming the cup has negligible mass, they make it easier for you to calculate lah. And there's no heat exchange with the atmosphere. Calculate the final temperature of water. Specific latent heat of fusion of ice is that. So heat gained by ice in melting, right? Change it to kilogram. That is latent heat of fusion. Multiply that. Then heat loss by water. That water there. Change it to kilogram times your specific capacity. 28 to minus theta. Right? That's the final temperature. So heat gain by ice plus ice water to temperature, the ice has to melt, and then the ice at 0 degree, the water at 0 degrees Celsius has to rise to temperature theta, and then heat loss by water. That must be balanced. So let the final temperature be theta. So that is your melting of the ice. There's the same as, but there's the rise in temperature. And then this one here, and calculate out. Okay, now anything not clear?
Yeah, I
Yep.
guess it's okay.
Say again.
It's okay.
You understand, huh?
But like I wouldn't know how to do lah.
You know how to do or not? Or
No,
you
no,
want
I
me?
mean I understand, but I wouldn't like know how to do.
That's why I want you to do the question so that
Mm,
you know how to apply the formula. No point
yeah,
in giving you tuition if you don't know how to solve the question.
yeah.
Okay, let's go to ideal gas. Right, will be cut off at any time lah. I still got about 2 more minutes. Right, under matter we will have temperature, and we are studying ideal gas now. And then 16 thermodynamics. Right? If you got during the break, you can try this question. Right? 15.1, the mole. 15.2, equation of state. Page 16, your note lah. These are equations that you need to remember lah. This is the equation of state lah. Alternative formula. Then kinetic theory of gas. 15.3. Right? Where we derive the pressure of gas. Derive this equation. Average kinetic energy per molecule. Right? We derive that. Use your own textbook. That's the syllabus. Very short only. Real gas has a complex behavior, but it is possible to make progress in understanding gases by developing a simplified model of a gas called ideal gas. A link between the behavior of gas molecule and temperature can be established. This provides an introduction to the concept of thermodynamic temperature, right? Latent ideal gas, the temperature, and kinetic energy of the gas. Right? Definition of 1 mole is the amount of substance which contains as many elementary units or entities as there are atoms in 12 grams of carbon 12. Right? 1 mole is 2 grams of hydrogen, 32 grams of oxygen. Entities can be atoms, molecules, ions, electrons, or other particles. Or you prefer the definition from the syllabus, you can use that. Right? 1 mole of substance is the amount containing a number of particles of the substance equal to Avogadro's number. Okay.